So today we wanted to talk about the IRIS dataset, more specifically on the the data, like the data pipeline, or sorry, not the pipeline, like the data life cycle. So we want to pick a data set. In this case, we're going to use the IRIS data set, and we're going to do a bit of analysis on it, visualization, modeling, and then maybe the post-modeling, a bit of analysis or discussion on that, so that we can kind of go through the entire process and we can get an idea of how to do that. This is our first video, and we're hoping to do more as we go. So I'll get right to that. And these are an empty Jupyter notebook that I've opened, and I want to create now a new Jupyter notebook that we're going to use for analysis using the IRIS dataset. So as we normally do, we import a few libraries that we might need. Import pandas as PD. Import matplotlib, pyplot for visualization as PLP, and I think this one you can also import NumPy as NP. These are the ones that we start off with, and we want to read the IRIS dataset. So data is equals to pd.read/csv file. And because I don't want to download the data, I have it ready here on GitHub. So I'll just copy this and I'll paste it here. And once we have that, we are now able to say data.head, and to be able to visualize or to see the first 5 data points. Okay, so this is our data. The data comprises of the sepal length, the sepal width, the petal length, and the petal width, and species. So these are output. And basically, what we want to do is to kind of visualize all this information. So here we'll also add Seaborn. Seaborn is a visualization library. It's built on top of preparation. We have our data and it's in the right format. So the next thing we'll need to do is to visualize the data. So here we can say kind of have a visualization and convert this into a markdown. So to visualize the data, we'll just do a scatter plot. So it will have the sepal length and the sepal width, and then we'll have the species. So here we can just say sns.scatterplot. Once we learn that, it's create an empty scatter plot, and we can now give it the data. Data equals to data, y is equals to sepal length, and x equals to sepal width. Then we add the color, which is the hue. This can be the species. So the plot will be differentiated. We can, okay, I'm getting an error here. Okay, I could not interpret. Let me see. So the y is the sepal length, the x is the sepal
I think
width.
John.
Okay.
I think there's a problem with the
yes.
The sepal should be the sepal length, not sepal length.
Okay, thank you.
Okay.
That was nice. Thank you, Alex.
You're welcome.
So this is how the data now looks like. I could not have seen that.
It's okay, it's okay.
Not sure if the data will work. I doubt, but okay. So, we can enclose it in a PLT. Figure, then PLT.show. And I can add this title there instead, so that stop giving us these errors. So php.title. Maybe it's good to have plots with titles. So you can just call it a scatter plot. And it's fine. So it's showing the various flowers. A flower can have a sepal length and sepal width, as well as the petal length and the petal width. So some of the, like for example, the setosa, they have very large width, they're very large sepal width. That's why they are on this extreme right side. On the other hand, the their sepal length is low, and the other two have higher sepal length and sepal width, but you find that the Vaginica is a bit on the higher scale in terms of the length. So now we can see that one of the main challenges of this is that we've only used information from these two columns. This is the first column, the sepal length and the sepal width. So that's why you find that the data is a bit mixed together, because we want the classes to be extremely clear. We want to see exactly where do we draw the line for each of the for each of the species. And right now we can assume our data as having 4 dimensions. So each variable is a dimension. And because the scatter plot only has 2 dimensions, that's why we can only use 2 of those dimensions. But now we can use a method for dimension reduction called the PCA. So here we're going to do a PCA analysis. It will help us reduce the dimensions preferably so that we can now visualize the data, and also we can use it for modeling. And we can import from Scalan dot preprocessing. We want to import standard scalar, and the reason is because data, being a linear model, it expects the data to be in a normal distribution. So we use the standard scalar to reduce the data into normal distribution. And from a scalar dot decomposition, we want to import the PCA now. So we initialize the scalar, and the scalar will be just the normal scalar. And here we need to specify what this will be our x. So first off, if you look at this data, you can find that the setosa have been, they are on their own, and then you find the other species on their own, and so on. But for the machine learning, we want the data to be shuffled. So we need to shuffle the data first. So we can say that data equals to data dot sample. If we sample the data, it will give us the data now back in a shuffled format. But we want to pick the fraction to be 1, meaning that we want to the entire data set. So the sample will include all the data, but now in a more shuffled format. And we specify what is our x. We drop the species from the data, so that will be our x, and our y will be the data, and this time we pick the species. So this is the data we have. So the scale data, or the scale data will be scalar, and we do a fit transform, and we are transforming our x, and now we can see what is the scale data. So this is where we were, and what we are saying is that we are going to reduce the dimension, and the first step of dimension reduction is getting your data in a normal distribution, and you normally use the standard scalar. So this is what I've done. I've scaled the data, and this is the scale data. Then now once we scale the data, we move on and we initialize now the PCA. So we can say that PCA equals to PCA. As we initialize this, we then we say that the transformed variable will be equals to PCA dot fit transform, and we are transforming the scale data. And here we can check what the transformed data look like. Okay, not dot head because it so it looks it's also an numpy array kind of thing, and there is these things that are called PCA. Well, the PCA, once it trains, it has an explained variance ratio, and these are the ratios that we have. And what this means is that the first um, column from the PCA analysis, it's also called a component, has 72% information. The second one has 23% information. The third one has 3%, and the fourth one has about 1%. So you can say that between the first and the second, we get quite a lot of information. So what we can do, we can just say np.cumulative sum. And once you look at this, you can see that I think we can also plot this. You can just say plt.figure. And we're not going to make a very good plot, actually. Just a line plot. Then, yeah, plt.show. So when you look at this plot, what is going on is that this is the first component. If we use just the first component, we'll have around 73% information. If we use the first and the second component, we are getting around 95% of information, and so on and so forth. So what we are saying is that by using the first two components, we can just say we are getting most of the information. So which is 95. So we've compressed the data from 4 dimension into 2 dimension, and we've only lost 5% of that information. So I think that's good enough. We can create a new pandas object so that we can now include this information that we have. I think we called it transformed. And the columns will be component 1, component 2, component 3. These are just the names for the new columns that we receive. And we can just say dt.head. We can see. So these are the components we now received from the PCA, and we can now include the species in this data. Since we did not do, okay, not I want us to pick the one after we shuffle the data. Yeah, should be data species, should be okay. And this is now how the data will look like. I'm hoping, yeah, we now have the species. So now we can visualize this data again using the same methodology we did up there. So it will be SNS dot scatter plot, and this time the data equals to the dt, y equals to c1, and x equals to c2, and then the hue equals to the species. Okay, yeah, okay, there is something weird happening. Okay, let me stop this. Something happened to our data. I don't know. Let me run this again. Okay, this is what I was expecting. From here, we can see that when you're using 50% of the information, only Setosa is showing like a difference. You can see a difference between Setosa, but for the Versicolor and Virginica, they are mixed together, meaning that their attributes are not bringing out that distinction. So if we were to like do any model, we will not be able to get a very good distinction. But down here, you can see that the Virginica are on the top, and the Setosa are extremely on the top, down below. And then in the middle, we are getting the Versicolor. This is what we were hoping for, that once we compress the data using PCA, we would be able now to visualize the data better in terms of dimension. And at the same time, it would help our models to create that split. So now we just go directly into the machine learning models. We just pick any two. And since this is just a simple introductory meeting, we'll only use the simplest of this. So from the scalan dot model selection, here we want to import the train test splits from scalan dot let's start with the linear models, and we want to import logistic. Yeah, and we give it a nickname or just LR so that it's simple. From scalan, I want us to import tree, and from scalan dot tree, I want us to import decision tree as our second model, classifier, and we'll import this as DTC for now. So these are the libraries we need, and also from scalan.metrics, you can import accuracy score.
Could you correct the import part before the accuracy score, please?
Okay, thank you. Yes, the accuracy score and confusion matrix. Thank you, Alex. Confusion matrix. Make it good now.
Yeah.
So here we start off with logistic regression. It's logistic because we want to do a classification. So if the output was numeric, we'll do a normal regression, but now because it's categorical, that's why we're using logistic regression. So we start with X-train and X-test, the Y-train, and
So,
Y.
John, can I ask a question?
Yes.
So, I know logistic regression is used for is a classification model,
Yeah.
but is it also, because I think in our context we are using it in the case of binary classification, but is it still applicable for a multi-class classification?
Actually, this in this case we are using it for multi-class classification because we have 3 classes. Let me show you. Even from up here, you can see we have Setosa, Versicala, and Virginica. So it's actually not binary. So we can use it for this kind of. We can use it for multi-class also. But of course, as the number of classes increases, the logistic regression is not your best choice. You have to use more powerful models, let's say decision trees, GBM, and so on.
Okay.
Thank you. Yeah. So here we just we're just splitting the data into training and testing. Okay, and we are saying that X train, X test, Y train, Y test, and we want to split the data, the X and the Y, into training and testing. And we can actually print, let's just print the X train dot shape and Y train, X test dot shape as well as Y train dot shape, and see if we have what we expect. Okay. Dot shape.
The name shape is not defined.
Yes, I'm writing fast.
Yeah.
So we have training data of 105 rows and 4 columns. And for the testing, 45 with 4 columns. And then for the Y, we have 105 with just 1 column. So that's why it looks like that. So let's go now into the logistic, and we can call it model equals to LR because that's how we named it. model.fit, and we want to fit the X train and the Y train. And then we are going to get a prediction from this model.predict X test, and we can now print out the outputs from this. And the first one is the accuracy score. And we are comparing the prediction and the Y test. And we can also create a confusion matrix for the same. Just changing this into confusion. So, it's very interesting. So here we are getting a perfect score. All the variables have been well predicted. So there's a problem here because again, when you see this kind of thing, you have to suspect that there is overfitting. So I think here what we can say is that let me shuffle the data.
Okay, John, I think there's that part where you what was this? Where
Yeah.
you can't recall. There's that part where you had to remove that line of code that I can't remember what it actually does, but I think it changed everything.
No. Which part? The ones that I shuffled here, up here.
Yes, where you had to shuffle the data. I think you removed that line of code, or didn't
Yeah, I
you?
removed it, but
Yes.
I'm shuffling it down here.
Oh, again.
This part, yes.
Okay.
Let me just shuffle it there. It's fine. I think we can increase the test size to around 1 and see if this changes. Yeah, this is much better because again, we don't want to see the model having that kind of perfect score. Of course, this data is simple; it can have a perfect score, so I don't see there is a problem. But I'm usually very worried when that happens. Maybe this is a 95% score, and we can see that it can only misclassified about 3. So one of the best ways to see how the model performed, we can use we can plot these kind of boundaries, how the model has plotted the boundaries. I have a function somewhere. I have a function that we can kind of use for this. It's a very long function, so I'll just paste it here. And what it does, it just picks in an X and a Y, and then the model itself, and then it is going to visualize it. And the model, the function is called plot decision boundaries. So we just say plot decision boundaries, and we're going to give it our X, our Y, and we're going to give it the model. So hopefully it visualizes for us. It's saying okay. Unfortunately, we need to convert the X equals to, and we can just import what. We can use a label encoder for this, and we can just say that encode equals to label encoder, and we can just say that our new Y will be equals to encode dot fit transform, and we are fitting and transforming Y. And here this can be Y1. Okay, reprocessing. So this is the plot now. As we can see, so this I think this was the Setosa. So we can see how the model made the decision. So for the yellow, there is a bit of about 3. This one, and this one. Those one have been misclassified, or at least the boundary, the way it has been split, is such that it can misclassify those. This is now on the training data, so that's why you find that this is not exactly matched with the testing data. But generally, this is one of the ways you can check how the model performed by plotting the decision boundaries, and you can be able to see. Also, you can use the accuracy score, the confusion matrix, the classification reports, and so on. So now we go to the second model, and we call this model 2. And this is the decision tree classifier. And we do the same. Actually, I think I can just copy this in the interest of time. Okay. And this will be model 2 dot fit and you're fitting X train, Y train, and this is model 2. And here, although the decision tree did not perform as well as the linear model, the logistic model, but again, we can see that the differences is not major. We can do the same here, but this time we just change the linear regression into the decision tree classifier. And now we can see that the way the model made the decision was a bit different. You can see that they are, instead of, this is not so linear. If you look at this, they are like very linear lines. So the model took the entire data and it's kind of fits straight lines in the data. And whichever data falls on one side, it's classified in such a way and so on. But now this one, there is no such clear kind of boundaries. You can find that although this one is a straight line, is a straight line, but you also find another one and some other ones that have been added there. So this is more non-linear kind of decision boundary. So again, another way maybe as we finalize is we might want to visualize this model in a different way. And for this, we can just use graphics. And this is because decision boundaries, this is not the best way to visualize a decision boundary, as we'll see. So again, the graphics is a way of visualizing machine learning models. Maybe if you have a deep learning model, you want to visualize it and that kind of thing. This is your best choice. So how you do it, you just say, let's call this plot, which is just a variable name. And we want to export a graphics object from a decision tree. And the decision tree is model 1. And the feature names so the feature names will be DP dot columns, or we can just call them X dot columns. And and the class name will be should be our what did you call this? Our data dot species unique kind of, yeah. And we want the field attributes to be equal to true. So let's run that. Okay. We called it model 2. Okay. Let me see. So model 2. So 3, and we want to export graphics model 2. I'll just add this down here. Feature names should be x.columns and class names Okay, I think this is the issue. It's actually a small thing. Okay, now we'll create a graph, the graph itself. And we use now the model, the library that we have imported up there, and we give it. Yeah, Alex, you have a question?
No, sir. No, I'm good.
Okay.
Okay.
So let's draw the graph, and we can now conclude. So this is what we are drawing up here. So how I'll explain it is, here we extract the decisions that the model made using the tree object, and we give it the feature names and we give it the class names. Down here, this one is just saving. We want to save the graph in PNG format, maybe for our documentation. Then here is just rendering. We want to render the graph, and which is this. And how we can read this is that we want to know how did the model go ahead and make these decisions. Of course, now we are going to have a bit of an issue because we are using the PCA object. So I think here we can, instead of using the PCA object, here I'll just use the data, and I'll say data dot, the x should be data dot drop species, like that, and this one can be data dot species, so that we see the decisions better. So here, like, okay, then if that changes, this one should be data dot columns, and we're picking the first to the fourth one, and this one can remain the same. Okay. So what we are saying, I think how we are going to read this is that the model made this decision, like if the petal length was greater or equals to 2.45, if this was true, then the model is pretty sure that's a setosa. So that's the decision. The brown is the decision. Otherwise, if it was not true, meaning that the petal length was either greater or it was greater than 2.45, this one went to now this node. And then for this node, it made a decision. It asked itself, is the petal width greater or equal to 1.75? This is the true, the false, and so on. So you can follow all these decisions until you finally get to the classes. These are the classes where the green parts, when they're giving it the class. So it's very sure. At this point, this is how the model classified the various flowers. So this is another way of evaluating your decision tree. And I think you can use it for even models like random forest and gradient boosting models. So again, guys, that's it. I think as a recap, what we did, we picked data. The data was the iris data set, and we did a bit of visualization. Of course, if it's a normal like data, you find the data is not so clean, so you do a lot of visualization and data cleaning and merging. And then we did a bit of feature engineering. In this case, it was a PCA analysis, but in some cases, you need to transform the variables. You might need to do a log transformation and so on. And for PCA, you need to do scaling. And finally, you do the actual PCA. And we visualize the PCA output. And down here, we visualized the final data. And then we tried two more machine learning models. The first one was the logistic regression, and we got the output from that. And we also plotted the decision boundaries. And then we tried a decision tree classifier. And then we plotted the decision boundary, and we found it to be a bit nonlinear. The performance this time was not so good, but we also wanted to kind of visualize the decision process of the model. And that's the final thing that we did here. So guys, is there any questions or comments so that we can finish?
Yeah. Okay.
But it's good to hear no question. Zomo, do you have a question?
Not really, just a comment. I think it has been an invaluable time well spent having to look at all those different steps. And I think these are steps that can even be replicated to any machine learning model out there that we may want to try, or any kind of data that we may want to use to get to this point. So thank you for the wonderful and making it in a simplified, easier way.
Okay, thank you, Zomo. The hope is that we all learn during these sessions, and everyone picks up something, even if it's small. But I'm glad that there was something that came out. James.
Okay. Also, I don't have a question, just a comment. Yes, maybe if somebody wants to look into other more, if you look at the nature of the decision tree, it shows that it's more of a forest. So I think maybe other libraries like maybe random forest, extreme boost might perform better than the decision tree, because if you look at how the graph looks like, it's more complicated. It has so many branches. So I think maybe things like maybe random forest will perform better, but it's maybe after some time, maybe somebody can try maybe decision tree and see how they perform. Things like random forest, things like extreme boost, because they will deal with complicated decision trees. I think that's a comment that I would make.
Yeah, it's a good comment. Actually, I picked the decision tree for its simplicity as well as the logistic. I did not want to go so much into details into the models, but I get your point. The models that are built on top of the decision tree, such as the random forest and the gradient boosting, they will perform. We naturally expect them to perform better. So, especially if someone was handling a more complicated problem like this one is a more simple problem, then they will need to actually think about those other models. So it makes sense. That's it from me as well, Alex. It was good having everyone. Thank you for your time. And I hope we'll see you next time when we'll be discussing something different. Thank you.